I am going to talk about how deep learning reveals the essence of Matt Damon. But this is kind of a more politically correct way of talking about it. Really, what I want to do is to prove that my face is not that different from a movie star's. Right? I look pretty good, and I'm going to prove it using deep learning. Um, and the way I mean, this is clearly as a megalomaniac, this is like something that drives me very strongly. But also, I also really wanted to use and learn a little bit of the next big thing in deep learning. So deep learning generally is sort of like lately really, really big, obviously. But within it, also there have been these sort of little waves of specific tools in deep learning, like recursive neural networks were like really big new thing like last year, 2 years ago. And what I wanted to really kind of like play around with was the next big thing right now, the big deep learning stuff of 2016, which is generative adversarial networks, which happens to be a really, really good way of generating uh, images that do not represent anything in the real world, but they do look like real things. Um, and I thought, since I really always have wanted to prove that I look really like a movie star, I thought, well, if I can show that my face is not that different from a movie star's, if I can sort of like show if you morph from my face to a movie star's, it's really a natural transition, then everybody will be on board with it. So let me first tell you about how this new next big thing works. The whole generative adversarial network stuff. It actually is like a framework with two separate models. There are two neural networks at work. One is the generator, the other one is the discriminator. Okay? Now, if you've seen Catch Me If You Can, Leonardo DiCaprio's character is trying to forge checks and stuff, like fake stuff, to get paid. And Tom Hanks is trying to catch him by figuring out like which ones are forgeries and which ones are real, right? So basically, Leo is trying to do fake stuff that passes as real, and Tom Hanks is trying to figure out which one's real and which one's fake. Now, but we are generating images, right? So in this case, Leo is basically a neural network that's supposed to take as an input just a bunch of numbers, okay, like a vector of 4 numbers or so, and using these, turn it into one image. The same set of numbers always creates the same image, but depending on how Leo's insides are working, what that image will be different. But basically, it's an image generator. Take numbers, make it an image. So it might generate an image like this, which doesn't look like anything. It might generate an image like this that kind of looks like a real face. With like these numbers might correspond to that, and other numbers might correspond to this, which kind of maybe looks like a face, but something else, right? But basically, it's a converter of numbers to images. And what Tom Hanks does, the discriminator, is as an input, it takes one image and says this is fake or real. That's all it does. It looks at this maybe and it says fake. Maybe it looks at this and says this is real. It looks at this and it says fake, right? Now, the way this whole framework that will end up generating very believable looking faces, and it doesn't have to be faces, but it's just one of the difficult problems that it's worked on, is we are going to train both of these networks. They are going to start as a terrible discriminator and a terrible generator. Anything that this generates will look like crap, and this will not be able to separate, just random noise from like a real face. But we're going to train them together, and it's going to be kind of like an arms race. All right. So, generator will try to be smarter and smarter in terms of generating new images, so that it can fool the discriminator, and discriminator will try to get smarter and smarter in figuring out what is fake, what is real. So maybe we'll start with, because it's a crap generator, it will just like make this and say, hey, this is a real image. And let's say we also have 200,000 real face images of celebrities and stuff. Okay, so we are training the discriminator by showing him real faces and these things and saying, hey, try to discriminate this. We are training it as a classifier. And it looks at this and maybe it says, hey, this is fake. And then we look, did this come from a real data set of faces or did this come from Leo? And yeah, it was fake. You were right. So he's really happy. Tom Hanks is right. And Leo is like, God damn it. Like, he keeps figuring this out. How can I fool it? So it actually looks on the insides of Tom Hanks. It looks at how is it figuring it out? What is it doing? And then it maybe figures out, it's looking at if it looks like a round thing, if the corners are dark and if it's orangish, right? Maybe something like that. And then, okay, if I do this, I can fool him. And indeed, it gets better. It fools the discriminator, and then the discriminator is thinking, God damn it, now I can't figure them out. How am I going to discriminate? Now it looks at the insides of the generator. How is he forging these? And then, oh, okay, this is not enough. All right, so I should check for something that separates these fake images from real images, and maybe it looks at, oh, the eyes are more well-defined or something like that. And then as the generator is thinking, oh, I'm doing so good, this is like, I solved this. Now the discriminator has wisened up and now figures out that these are fake. And then the generator is like, oh, okay, how is he figuring it out now? Oh, the eyes and stuff. So it starts generating images like this, and you keep doing this over and over again like a million times, and suddenly this generator is generating images that are very difficult to distinguish from real faces, as even us human beings as discriminators. So this is how you train an image generator that can convert just a bunch of numbers into an absolutely realistic looking face that does not exist on this world. Okay. Now, of course, this is generally the framework, how you train them, yes.
So I have a question. So you're assigning some sort of point value to saying like, oh, you're doing good or you're doing bad, like to these neural nets.
Sure. We'll get into a bit more details, but basically the discriminator it's a classifier that takes an image and tries to get out a probability of realness, right? And it's a neural network, and you are basically it has a bunch of weights in it. It's a model with a whole bunch of parameters that you're optimizing as you go. But the trick to the optimizing is that while you're optimizing the parameters of the generator, it looks and tries to figure out how this guy is discriminating, and you change the weights of this such as to fool this guy. But basically, these are two models with a bunch of parameters that you're adjusting, optimizing the parameters a little bit every time you go. And I'll sort of like get into more details. If it's still not clear, let's talk about it a bit more. Okay, so let's first focus on the discriminator, all right? Let's see how Tom Hanks is trying to figure out what's real and what's fake. It's a bit simpler. And I am going to use the example that's a bit simpler than just faces. Let's say that we've all went to the optometrist. This is our eye doctor. And he is like a really, really tricky one. He is trying to actually fool you. Like, he thinks he's really funny. He's really annoying. And this douche is showing you these things and says, hey, read the letters. Okay? What he's done there is actually not all of them are real letters. He's like, some of these are just garbage. He will think that he's blind. Okay? Now, you probably can't see this. Let me just zoom in a little bit. These are basically, you probably can't see it. Okay, look at this. This is what they look like. Okay, these are like 9-pixel black and white images. Some of them are like weird. This is not this is nothing. This is like, that's a real one. That's O. This is X. That's H. That's nothing again. This is another fake one. That's C. Nothing. Y. And some weird stuff. Okay, so basically these are the fake ones and these are the real ones. The reason that I went to this is because like I made the problem a bit simpler, but it's the exact same problem. It's just like 9 pixels instead of 64 pixels, and it's just black and white basically. Each of these is one value between 1 and 0 basically, like how gray are you, right? So it's just a bit simpler, but it's the exact same problem of how do we figure out which ones are fake and which ones are real? Well, we use the magic of classification, right? So basically, if we already know a giant labeled data set where we know, oh, this one's fake, this one's real, this one's real, this one's fake, we can just train a classification algorithm. It's a supervised algorithm, and then it will just figure it out. This is just like very general data science, right? we're going to train a discriminator, and then as an input, it will take an image, and it will say it's either it will classify it as one of the two classes, real or fake. Okay, it will look at this and it will say fake. That's the idea. Now, a very common classification algorithm that has been around for like a little long time is, logistic regression. This is just a way of representing a logistic regression algorithm where you have a bunch of features about your elements that you're trying to classify into either A or B, or real or fake. You put them into logistic regression, which combines them in a linear sum, puts it into the logistic function, and gives you a probability of it being real. And basically, if the probability is like higher than 50%, you say, I think this is real. If it's lower than 50, you say no. Okay. Now, what are the features going to be? Well, these, like I said, are basically just numbers. So each of these pixels is a value of how gray or how black this is. So these are just like, each image is just a bunch of matrices of numbers, right? So you can just say, all right, each of my features is like how gray each pixel is. 1 pixel, their value is my feature, right? So it's like 9 features, logistic regression, it gives you a probability 80% real, 30% real for these numbers, something like that. Now, the thing is, logistic regression is a very simple algorithm that will not be able to catch complex local and nonlinear relationships. So this will work somewhat with just these 9 pixels, but as you go to like bigger and bigger images and stuff, like this will just, you won't be able to tell if something is real or fake just by locally looking at a single pixel and if this is like really black, this is highly probably fake. You can't say that. You need to look at more coarse-grained local, you need to look at lines, objects, like how the eyes look, right? So logistic regression by itself is not going to cut it. So what we're doing is that whole, it sounds super mysterious, the deep learning, but basically you could just think of deep learning as logistic regressions of logistic regressions of logistic regressions, right? So what you're doing is instead of putting these 9 features into one logistic regression, you will in the end have one logistic regression that will give you a probability. But first you sort of like take some of these, and when this gives you a probability, it's the probability of that some hidden feature existing or not. For example, imagine 3 pixels right next to each other, right? If all of them are black, then you could say there's a line there. If not enough of them are black, then you can say there is no line. So maybe this is a feature of, does this line exist or not, right? So it will basically add them up at some weights. It will figure out what weights it needs to figure out if it's a line or not. And maybe these are different lines. Maybe you combine these different lines. If these 3 lines exist, maybe there's a triangle there or not, right? And basically you keep sort of, these logistic regressions of logistic regressions are, instead of directly trying to get to the final result of the probability of realness, you first try to figure out some hidden features, which we don't know what they are, but you try to figure out features from these pixels that will help down the line figure out what is real or not. So, and there are a million different ways of doing logistic regressions of logistic regressions. This is, as you can see, the topology of this network of which features are you putting into which logistic regression is, you could go like a million different ways. And usually the different part is figuring out what topology works or not. And for image processing, quite a long time ago, we figured out that this idea of convolutional neural networks works the best. And what that does is basically kind of think of it as coarse graining. You're trying to look at regions of an image by itself, as in, okay, this logistic regression is going to take as an input just this part of it. This guy will take this part of it, this guy will take this part of it, this guy will take this part of it, and they will figure out basically some features out of these. On the next layer, I'm going to say, okay, these 3 guys are going as an input to this, these 3 guys are going as an input to this, and then these guys go in as an input to that, right? Basically what I'm doing is, yeah.
Oh, sorry, I was just wondering, so does that mean that your regions and your hidden features are something that you define upfront for the neural network, or is that something that it figures out after running simulations?
What you are determining in the topology is how many pixels, or like which sort of submatrix is going as an input to this guy.
Okay.
But you are not saying, hey, take this pixel, like look at this pixel's weight 5 times, look at this one's 1 time. You're not trying to figure out what feature it's going to be. It's going to figure out those weights, like how much it's multiplying each of these with. It's going to figure out itself. So you have no idea how these 4 pixels are going to turn into that 1 pixel. You don't know. That will be during training, just like figured out during the optimization process. It will be a black box to you. What you are determining is what region of pixels are mapping into what picture.
Okay.
And these basically kind of look like you go from a 64 by 64 image into 32 by 32 weird pixel stuff. Those pixels are no longer like just visual pixels. Maybe they are edges, maybe they are lines, maybe they represent something else, but that is up to the neural network to figure out.
Thank you.
Okay, so now one difference, I said that these are all logistic regressions. In deep learning nomenclature, logistic regression is basically, it's generalized a little bit more, and it's called a softmax activation function. Basically those sigmoid S stuff. And you do need to have one of those at the end because those functions map to basically take anything from -infinity to infinity and map it to between 0 and 1. So it gives you a probability. So you need to have one of those at the end. But if you use some other functions in there, it works better. We found out recently that rectified linear units, which is basically like, hey, if when I add these up, if the sum isn't big enough, just don't fire. Just give me 0. And if it's like above some threshold, just give me however big it is. Something like that. But the idea is the same. I mean, you basically have an activation function. Instead of sigma, it's something else, but that's what you're doing. And this is like this really toy, small 9 pixels into 4 into 2 into 1 type of like little optometrist problem that I showed you. This is taken actually from the DC-GAN paper, the main paper at the beginning of this year that first like did it really, really well with images. And this is what you're doing. You're taking a 64 by 64 pixel image times 3 because there are 3 colors, red, green, blue, right? You are basically doing that convolution of like 5 pixel by 5 pixel into boop, 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 boop. And you're doing this like 64 times, so you basically have a whole bunch of nodes. And then you do it again, you convolve this, you do convolution on this, on this. Basically, this is a blown up version of what I just showed on that toy example. Okay? And if you are remembering, this is our discriminator, which takes an image, all these pixels with red, green, blue, and gives up one single number, which is a probability of real or fake. Okay. So this was the discriminator. And the generator, which takes, let's say in this simple case, like maybe it takes 2 numbers between 0 and 1 and turns it into one of those 9 pixel images, right? Maybe this vector turns into that, that vector turns into this, these numbers turn into that. And this is how it looks like. It's basically the exact same thing. As an input, you take, in my case, it was 2 numbers. For bigger images, it's like 100 numbers. It takes a vector of 100 numbers, and it turns it into a 4 by 4 times this many nodes, these many features, then makes it 8 by 8, and this many, 16 by 16, etc. Like it's just a reverse. You take 100 numbers, you end up with a 64 by 64 by red, green, blue image. Okay, so that's the topology that works. Like I said, it turns out in the last maybe 10 years or 5 to 10 years, we have been in deep learning spending most of our time on pretty much 2 things. The whole idea has been there forever, but now we have computers strong enough to actually calculate all that stuff. But also, we are working on what topologies work well. That's the one thing. And the other thing is, how can we train them faster? The training algorithms. Those are where the research is happening. Okay, and you know all this like complicated deep learning architecture, you can code this in Python very simply. this is like 1, 2, 3, 4, 5, 6, 7, 8, 10 lines of code is the discriminator. And basically, see this, the H0, H1, H2, these are the 4 layers that we saw here. These are the 4 layers. Basically, what it says is, hey, the first layer is the rectified linear unit, this function, with convolution 2D of take the image with this many dimensions, and this is its name, right? So it's actually pretty straightforward. And the code where I do all of the stuff that I'm about to show you is like, it's all open source. You can look at this link. It's also on the meetup page. There's the link to the code on GitHub. You can just like play around with it yourself. And also, I didn't code all of it. Tae-Hun Kim actually coded that DC GAN, that whole framework already in TensorFlow. I just used that. Brandon Amos wrote like a really nice blog post about doing something else with it. I used some of his code. You know, it's pretty easy to just like take all this open source code and just like add 10 lines of yourself and get stuff done immediately. Okay. So we went through how this whole thing works, and it just generates images, right? In the end, basically, you do all this, and once this is all trained, you can just randomly pick 100 numbers, give it to the generator, and tell me what does these numbers look like as a face. And it will give you a face that looks real. So I did that a bunch of times, and here is a sample of the faces it generates. Okay, these are all generated by the generator. I trained it with 200,000 celebrity faces. There are a whole bunch of celebrity face data sets that are freely available online. I mean, some of them are like, this is really scary. Some of them are like really weird. But I mean, look at this. These look super real. And this person does not exist in real life. So it's really cool, right? Here's another set of fake faces. Again, some stuff of the nightmares. But look at this dude with the sunglasses, right? It's really cool. Okay. And doesn't understand noses very well, maybe. And this is my final set. Again, you can see all these like different faces that not all of them are great, but also maybe if I trained it with more images and for longer and stuff, it would have worked. By the way, training all those things, if you're doing it on a GPU instead of a CPU, you can do it really, really fast. So if you have an NVIDIA graphics card, all of this actually takes like 20 minutes. And if you don't, which is totally fine, you can still do it on CPU if you just install TensorFlow from its like just regular stuff. This will happen in about maybe 3 hours or something. I mean, depending on obviously the properties of your computer. But like, I mean, it's amazing. It's pretty fast. So now, like I said, by itself, I trained this. A lot of other people have done that. Like they've trained their own DC GANs. By the way, computer scientists love these acronyms. So, and I've been working with this for so long that for this kind of stuff so long that I keep like using this. So sorry about that. It's really stupid. Like that. Remember that rectified linear units, which is basically just 0, 0, 0, and then x equals y line, right? That's a rectified linear unit. If you do it a little bit differently, it's a leaky rectified linear unit, and they represent it by LR, like capital R, E, LU, like it's completely obfuscating. It's crazy. And DC GANs are basically, GAN is the Generative Adversarial Networks. Adversarial because it's an arms race. Generative because it's generating images. Networks because it's neural networks. And the DC part is basically, it's because it's using convolution. Okay. Now, this is the coolest part. This is the best part about it. I mean, you give it a vector and it gives you a face, right? But take the same vector, just change one number slightly, and the other face is very, very similar. All the faces are mapped into a linear space of those vectors. So, which means you can do math with them. You can take vectors of smiling women, subtract a vector of neutral woman, and add a neutral man, and you get a smiling man. It's amazing. That's the best part of it. And look, you take the person with the glasses, subtract man without glasses, add woman without glasses, you get woman with glasses. It's unbelievable. The first vector arithmetic with deep learning stuff, they did it with language analysis, and they did that whole word to vec stuff. And some of you maybe remember about the whole, you take king minus man plus woman, you get queen, right? This is basically the image equivalent of it, and it's amazing. Okay, so now I basically explained how all this stuff works. Now we're coming back to the origins of my interest, which are completely, megalomaniac. As I said, I'm a megalomaniac. They're very narcissistic reasons. But I want to see, hey, Leo, generator, what numbers would represent my face, right? And are they actually really far from, an actual movie star's face? So if I can convert real faces to vectors, basically go backwards instead of here are 100 numbers, give me a face. Which numbers represent this face, right? Then I can do math with it, and I can sort of figure out how close it is to others. And to be honest, this whole idea of representing faces, basically, let me show it to you like this. This is what the generator does. What I'm wondering is which vector will give me this, okay? And this question is not new. These generative adversarial networks are new. I and Goodfellow, this totally nerdy and very unhygienic looking guy, very smart though, super smart guy. He came up with this idea at the end of last year, and basically this year this blew up. And it generates much better looking images than anything that came before. But there's another whole set of generative framework that uses deep learning that tries to answer the same question. What they do basically is, you know how with the discriminator we go from image to one number, and the generator is going from 100 numbers to one image? There's this autoencoders, variational autoencoders. What they do is, let's take one image, start with the image, go down to 100 numbers, which is way less information, and then go back up to an image and try to optimize it so that the final image is as close to the initial image as possible. That way, the 100 numbers in the middle will be a good representation of that image, right? Which also kind of works. Like I said, it's a more natural way of trying to figure out that vector that represents your face. But the generated images at the end do not look nearly as good as this framework. So now what I was interested in is, now that we have a much better working thing, how can I represent my face with numbers? Okay. Now, what I'm hoping is I can just find this vector that will produce something as close to my face as possible. It might not be exactly the same thing, because the generator, of course, is limited to some subset of all images that can be generated. But that's the idea. Now, what can I do to get this? Well, I can start with a random vector that gives me a completely unrelated face, right? And then I can actually define a loss function saying, hey, take my face and look at the differences in pixels, right? And try to optimize, try to move a little bit in this linear space, try to go find the vector that lowers this loss, right? So basically take one step, change this vector a little bit so as to make the pixels closer to my face's pixels, right? And I will basically define this loss and run a stochastic gradient descent algorithm on it so I can find the vector that's closest to my face. And one little tiny interesting detail there is, instead of just trying to minimize the differences between the pixel values of my faces, I also want to punish it if the whole image looks really fake. I want to basically I'm saying, instead of try to give me the exact pixel by pixel match to my face, I'm trying to say, hey, give me a very realistic looking face that's closest to my face. That way it won't be like this really blurry, weird stuff, hopefully. All right, so here it is, a bunch of my faces, all looking amazing. I'm going to start with random vectors, completely randomly chosen, so completely unrelated random faces. I'm going to say, okay, let's slowly, step by step, try to get closer to my face by changing that vector a little bit, looking at what that image is, and find the closest to my face. So here goes. This is how it optimizes. Slowly, as those vectors are changing, these faces become closer and closer to my face. Now you can see that it's definitely not perfect. And what's really interesting is that, for example, here I'm wearing glasses, right? And here, this is kind of close to my face, but there are no glasses. Because probably the way it represents glasses, we have seen that it can actually show glasses, but the way it understands that like high-level feature is kind of different or far away enough from the space that it can get better with my eyes, but if it's trying to do that, it cannot mimic a glass really well. So, and you can see again, like it really, really fails because of where it started in some cases. And here, let me show you another case where I started from a completely different set of random faces. Okay, and also this was like I tried to get something much faster, so this is like larger steps, so it will not equilibrate as, but you can see that it's struggling a little bit. But now you can see, for example, it keeps going between glasses and no glasses, and in some cases this produces, because it started from a different random set, better faces, and in others it just still can't. Okay, so now I have basically, but I've done this, and I can take the final vector of this run, and that's basically a way to represent my face, right? Now I want to do the same thing to Matt Damon. These are all Matt Damon faces, and these are random faces that I'm going to start from, and they're all becoming Matt Damons. So I basically have a Matt Damon vector for different angles of his face for all these different samples. And I'm going to do the same thing for George Clooney. George Clooney on the left, random generated faces on the right. These are real, these are generated. We're trying to find the vectors that are closest to these real faces. And it screws up some of those, but pretty good. And now we come back to the whole idea of that's me, that's Matt Damon. I figured out which vectors these correspond to in the generator, right? So now, if I start from this and interpolate to this really, really slowly by showing all of the middle images, then my face should morph into Matt Damon, and it won't morph a lot. It's going to be very natural transition. You'll be convinced that it's pretty much the same face, even though I have facial hair here and he doesn't. Okay? All right, are you ready? This is the big moment. Okay, here we go. That's turning a little bit demonic in the middle, but all right. That's Matt Damon. I mean, what's interesting is that a lot of those middle stages are basically other vectors, and they all still look like believable faces, and that's the whole power of generative adversarial networks. Okay. And I didn't stop there. I should have, but I didn't stop there. And I thought of this. Okay, I can actually find the vector to each of these different pictures of my face, right? So if I average these out, remember all the math stuff? If I average these out, I will find the one vector that carries like the essence of my face from every angle and every light, right? That's going to be the one vector that we can look at the image of, and that's the essence of Irmak. Okay, I was really excited about this. Here is my essence. The essence of Irmak looks like a shady guy with a goatee. And I did the same thing to Matt Damon and took the average of all those faces that you saw. And this is the platonic Matt Damon. And this is the Eigen Clooney. Okay? And one thing I unfortunately noticed is that these movie stars' essences look a lot like each other, whereas that's very different from mine. And I was sad. And that was the end of my research there. I just stopped. So that's how you use generative adversarial networks to generate images. And it's all quite easy in Python using TensorFlow. And check out the code and just run it for yourselves. Yeah, you had a question?
I just wanted
Oh, cool. Thank you.
I do have a question.
Yes.
Is the goal to make a good generator or to make a discriminator?
Sorry?
Is the goal to make a good generator or to make a good discriminator?
The goal is to make a good generator. I mean, building a discriminator is the easier problem.
So is this successful at building good discriminators as well?
Yeah, and people are, so one thing that people have just started to, it's a really recent paper, they've just started to use this to understand the inner workings of other classifiers. For example, somebody did a not safe for work classifier for images, right? That's Yahoo, I think. Yeah, Yahoo made that. Basically, they fed it a bunch of porn and regular nature stuff and said, just like that discriminator, basically, they trained it. Like I said, by itself, making a discriminator is somewhat of an easier problem than making a believable generator. But what's really cool is that it's still a black box. I mean, there was a Deep Dream and that kind of stuff that tried to understand what those hidden features are. Oh, maybe if we just like amp up this middle feature, oh, it looks like squirrels everywhere, right? That was Deep Dream. And now that we have this framework, what they did is they took that discriminator and put it in a generative adversarial network like this, and then trained the generator part of it. That way, they can tune and say, hey, what if I'm trying to generate porn, and I'm trying to mix beach pictures with like the porn part turned up, and then you suddenly see beaches with like a lot of phallic objects in there, or like the water looks like vaginas and that kind of stuff. So it basically helps you understand, for example, by plugging in the generator part, what the discriminator is doing, which was just like a separate thing. Mm-hmm. Yeah.
So when you were originally training the discriminator, you have it knows what a face is by like some data set of faces, your 200,000 faces you put in. What were the non-face data set?
So you don't. So when I explained the discriminator, because I isolated those two and explained them separately, I was talking about how, for example, if you're trying to figure out which letters are real and which ones are fake, you just have a data set of the real and fake images, and then you just give it to them, right? Now, but for the whole generative adversarial network stuff, you train both the generator and the discriminator at the same time. You start with both of them not knowing anything. The real faces that you're showing it and saying these are real are coming from a database of actual faces. The fake ones are the current creations of the currently stupid generator. And every once in a while, you give it an image from the generator and say, is this real or fake? And you sort of like, it says something, and you say, you were wrong. And you're training it with like, no, this was fake. And every once in a while, you give it a real face from the data set. Mm-hmm. So the fake ones are coming from the generator. The generator at that stage of training.
And so does the ratio with which you feed it true versus fake, does that matter?
It matters as much as like if you put a ton of imbalance, usually you just do like 50-50-ish. If you put a ton of imbalance with any general classification algorithm, it's a bit harder to figure out the right model of discrimination. So because the problem is easier if you give it 50-50, and because we have control over that, that's usually what we do. It could handle if we gave it like 40-60 or something, but if we did it 1% and 99%, it would just be harder to train. So,
and so you have basically +1 every time the discriminator gets like the true image, and then every time you're not sending a true image is a fake one.
Yeah. So with stochastic gradient descent, what you're doing is basically, so let's say you're trying to fit a line to a bunch of points, right? If you in Python do scikit-learn, hey, just like fit me a linear regression, what it does is obviously gradient descent, where at every step, it's looking at every single point, right? So if it was an image classifier, it would be looking at every single image that we would give it and calculate the derivatives and take one step. In stochastic gradient descent, you're doing it like with like tiny batches of like just one image by one image. So because the training is one image by one image, it doesn't, you can also think of it as you ask it a question and you tell it if it got it right or wrong, and it adjusts it. That's one way of looking at it, but you could also think of it as just like regular stochastic gradient descent, where instead of asking a question and saying you're right or wrong, we are just saying, hey, here's an image and this is fake. Adjust.
I see.
Yeah.
Would you use this for facial recognition? Like, you train a bunch of like faces to get the vector form and then take an input from somewhere?
So we've gotten really good at facial recognition as well, and those are a separate classifier. What they do is, so what I did is basically I'm representing this image with 100 numbers, right? You can think of it as one type of representation of an image. Facial recognition works better if you specifically figure out the features like, oh, the arches of your brow. And I mean, we still don't know. That's another neural network that figures it out by itself. But it usually, you are turning a face image into just, is the light value increasing in this direction or not, type of, like, you do one transformation yourself and give it this gradient of light, and it figures out what to look at, like the arches, the nose width, that kind of stuff. It figures out itself. And that set of numbers, instead of these 100 numbers that are good for generating, end up being better representation for us to be able to discriminate faces. You could use these vectors to use these 100 numbers. It would just not be as efficient as the ones that were specifically for that reason. Yeah.
So I'm just kind of like sitting here watching this. I'm kind of caught in between, like, on one hand, this is like incredible how far this has come, but also obviously, there's still a ton of room for improvement. Mm-hmm. So my question is, is it known, like, what the limiting factors are of the whole process right now? Like, I mean, is it the 100 number vector is too small? Is it maybe the framework with the architecture of the network? Is it known, like, what can be improved?
I would say generally no. Like, what happens with these things is, let's say image classification. Let's go back like 15, 20 years, right? Before we figured out the whole convolution thing, what we were trying to do was put every single pixel. We would make, 10 layers of hidden features, and let's say 10 layers of all those nodes of logistic regressions, and into every logistic regression, I would link in every single pixel. And we were doing fine. I mean, it was all right. But then once people figured out, oh, when we do this convolution stuff, first of all, we can get away with actually models that have way fewer parameters, and the way that the activation functions that we use, and this specific type of backpropagation algorithm, which is like how you go derivatives all the way back, right? As we kept figuring those out, we suddenly made like these huge jumps. And before any of those jumps, nobody could tell you this is what's going to solve the problem. So I would say probably if we had faster machines, we could just like stronger and stronger versions of this. Instead of just 64 by 64 pixels, I can do it with, a giant 4K pixels maybe. But we don't know where the next big thing is. One thing that George Hinton, one of the biggest names in deep learning, is working on, is this idea of our eyes. When we process images, there are these like weird column-like structures, and he is trying to sort of like develop this new framework that takes a different approach, and instead of like these generally deep things, it's kind of like, imagine separate columns that in the end like sort of link up. Right. That's like a really interesting thing that is inspired by biology. He can't get them to work well at all. So maybe he will get it right one day and it's going to be amazing, and maybe it's going to be something completely out of the left field that we don't know right now. Yeah.
Do you ever have to account for the case where the generator just completely by accident generates something that is exactly something from your database? Or is the probability of that just too low to matter in the long run?
Well, I can tell you this. When first they started building these, like the idea comes up and they are training it like this, and then the images come up and oh my god, these look super real. What the initial researchers thought, oh, we screwed up. What it's doing is it's memorizing the initial data set, right? And it's just figuring out exactly which parameters to set so that it can reproduce the exact same. It is not generating new faces that do not exist that look realistic. It just reproduces some of these things, and we cannot look at every single face because there are like a million of those. But then what they did is, okay, for all these generated faces, let's look at the nearest neighbor, like the closest pixels, and see if it's identical to something in the data set. And they weren't. They were close to real faces, but they were quite different still. And it turns out they do not replicate any of the original faces. Interestingly, they come close, but interestingly, they cannot reproduce it exactly the same. And as in my case, which is kind of, I'm doing it a bit more sloppily fast, etc., but you can see that none of them ended up, like, even if I was trying to find the closest to the face that this generator can generate, none of them got it exactly right, just got really close.
I'm curious on this data set that was trained with people's faces. If you took a picture of a cat's face
Yes,
and brought that back into a vector,
it works.
yeah?
It works with, they did it with birds, they did it with bedrooms, interestingly. They did it with, like, and also, remember how when I was like doing these morphing from one vector to another, everything in between looks fine? Like when you do it with bedrooms, for example, a window slowly morphs into a TV set or something like that. It's like these really interesting, all believable transitions between different bedrooms type of stuff is happening. When we try to do it with like a much wider, not as concentrated sets, like, hey, let's just take 10 million Google images, all random, and put it in, then it fails. Then it starts doing these weird shapes that are not realistic at all. So it cannot right now just learn an entire random image generating stuff. But if you keep the data set to something like faces, cats, birds, grasses, like nature vistas, it works. Yeah.
So do you have like a video card sitting in your garage or something?
An NVIDIA card? No, I did all of this on CPU. I didn't use a GPU. I mean, it was slower, but it was totally doable.
And then why NVIDIA? Is that because it supports CUDA or something?
Yeah,
like
it's
that?
all, yes. There are a whole bunch of deep learning libraries built on CUDA, and when you install TensorFlow, they ask you, do you want to install the TensorFlow that works with the CUDA stuff that's way faster, or do you want to use the regular one?
And then I see people renting out. I think AWS too. They started renting out GPU.
Yes.
Do you see any trend outside of the Amazon world of doing that?
It's still pretty, oh yeah, it's not just Amazon. The Google App Engine is also doing that now. They started basically, yeah, when you're getting a cloud server, you can say, I want a GPU server, which has like a really good graphics card in it. You could even get a cluster of those GPU ones, and just like TensorFlow also has a version that knows how to utilize multiple computers in parallel to train these kind of things. So yeah, with AWS, and I think Microsoft is about to do the same thing as well. So all of those cloud server services are about to start offering you all these virtual machines with good graphics cards. Yeah.
You had 200,000 images of Matt Damon, right?
No, I have only like maybe 200 of them are Matt Damon.
Okay. How many of yourself did you have? And what was your experience using, like, trying different sizes of data sets, if you tried it?
So I trained the generator with 200, because 200,000 is about the regular median size of these data sets that are out there. They vary in terms of how many faces of the same person are in there. Some of them are just like 2 of each person. Some of them are like 500 of the same person. But it's 200 images. That's how it learned what a face is. And I didn't put my own faces in there. And then when I was trying to go like this way, given a face, what's the representation, right? Basically you saw, this was like, these were the number of pictures on Facebook that I had that had like mostly my face in it. So I just took those. I'm sure especially when I was doing the Essence thing, also like the Matt Damon and George Clooney had more images in it. If I had a few more of my face, maybe it wouldn't have looked so shady. But
So did you try like different size convolution windows, different size?
I didn't, because you'll see there are like now 50 papers or 100 papers or 50 big papers on this framework. All of them are using the exact same architecture because, like I said, the big difference makers end up being in the topology and in how we train them. How we train them right now in the last like maybe 2-3 years, we've been doing the same thing. Once you figure out that this topology works and this gives good results, people just stick with it because if you change it a little bit, usually it works, worse. So there's that one paper at the beginning of the year that just said, okay, and that was the bedrooms one. We did it with this topology. It works really well. And then this entire year since then has been using the exact same 64 by 64 pixels, that many convolutions with 4x4 windows. You can also change the way you're doing convolution. There's convolution arithmetic, like you can just do sliding windows of 4s. You can do, some padding in between, all of that. So they figured out something that works, and we're just sticking with it. Yeah.
Will that scale up? I mean, so you say 64 by 50. Will that scale up to larger images, or do you have to refigure out the topology for a larger image?
So technically, there's nothing that would stop it from working with 4 times as big images. It just because there's so many more parameters, it would be way slower. And I think usually when people do research, like if you just say, hey, I took the same thing and I did it with bigger images, you are not going to get published on a big journal. I'm sure those will come, but like probably in a year or two. Usually the people at the forefront of the research are trying to figure out, okay, what other interesting way can we use this? Yes.
Did you explore like finding an attractiveness vector and then adding it to your own face?
Good idea. My next project. No, honestly though, actually, like once I started doing this, I formulate this with like my motivation is to morph my face, but really, it's more of I want to get my hands dirty with this framework type of thing. Actually, for this this motivation, there's a better way of doing this, which is use the face recognition software. It's also Brandon Amos has made it all open source. There's this thing called OpenFace, which you can again train in 20 minutes with your face and some other people's faces, and it will start recognizing them out of the pictures. So what I would do is actually use the face recognition software, to map my face into other set of numbers, basically the set of numbers that the face recognition software thinks of a face in, and then do it with Matt Damon, with George Clooney, right? All of them, turn those into vectors. I should go with Robert Downey Jr. That's a closer one than Matt Damon. And then maybe do like an ISO map or like map those vectors of many numbers onto 2D and see where they stand. It will probably be something like, I am here, Robert Downey Jr. is like right next to me, very close. Matt Damon, George Clooney, right? Something like that. And maybe from those vectors, which are more of what a face looks like, rather than how do I generate new images. And there, maybe you can do like, if you think yourself capable of ranking people's attractiveness, accurately, then you can actually build another model that tries to predict attractiveness from those features and see what grade you get. Good luck. All right. Any other questions? Cool. Well, thank you very much.
Thank you.